Hey everybody, we're going to continue now with section 3.8. We spoke about in the previous videos. We talked about limited growth, unlimited growth, but sometimes it's a sort of a combination of the two. So let me show you what I'm talking about. I'm going to share my screen with you, and this is a direct quote from the textbook that we talked about unlimited. So when we talked about population, we used the unlimited growth model. But sometimes the population is going to be constrained by food, space, or other resources or things, and sometimes the population can grow both in proportion to size and relative distance to some maximum, and that's called logistic growth. So let's take a look at that. Here's the official definition right here. So logistic growth follows this formula right here. So if a quantity grows at a rate proportional to its size and the distance from a maximum value, m, m is the maximum value, it can be modeled with logistic growth, which has a differential equation y prime equals ry times 1 minus y over m's, and that is 1 minus y over m. So all these equations are a little bit similar. One was the first one was the simplest one. Y prime equals ry, and they changed. But anyway, that's the differential equation. Now the solutions to the differential equation are going to want it being this: y equals m over 1 plus a e to the negative rt. Let's bear this in mind. Let's look at some problems now. So I'm going to go back to. I'm going to stop sharing my screen. I'm not sharing anymore. I'm going to go to our paper and we're going to do some math. Okay, here's a problem. A colony of 800 rabbits, that wasky rabbit, is introduced to reclaimed forests. After 1 year, the population has grown to 300. So it started as 100 and grew up to 300. It is estimated that the forest can sustain 5,000 rabbits. So again, it's not like the problem we had before with the population in the previous video, where it just kept on growing and growing and growing, because we're 5,000 is the max. And it could be that the forest only has so much land or food. It could be once there's more than 5,000 rabbits and start to die, whatever the reasons are. The Forest Service plans to reintroduce wolves to the forest when the rabbit population reaches 3,000 rabbits. When will that occur? Okay, so we don't need to know that they're going to introduce wolves. We just need to know when is it going to reach 3,000. So let's go to our paper and let's work this out. All right, I'm going to stop the share and I'm going to go to my paper and work it out. Change videos. I'm going to change videos. Change cameras, I mean, and we want to get this as a. All right, perfect. Okay, very good. So let's solve this sucker. So first of all, in our problem, m, the maximum, is boy. In our problem, m, the maximum, is equal to 5,000. That's what they said. 5,000 was the top. So m, let's get that down. M equals 5,000. Okay. And we started. So y of 0, meaning the population at the year 0, and the year 0 just means the year that we started this, was equal to 100. And we also know that y of 1 equals 300. I just want to review the basic facts. So the population at the year 0 was, at the outset, was 100. After 1 year, it was 300, and the max is 5,000. So I just want to get the fact out. And our question is, so the question is y of what? So the question is y of, I'm going to write w, y of what is equal to 3,000. That's really what we want to know. So what year are we going to, or when, when I say what year, it could be after, it could be, it doesn't have to be a whole year, it can be a fraction of a year, whatever. So when is it going to be? Now, we learned that the differential equation for this is y prime equals ry times 1 minus y over m. And R, oh, by the way, I didn't say what R was. R was the growth rate minus constraints, meaning how the population would grow if there wasn't any kind of maximum value. So R is the like unrestrained. So R is what it usually was. And we also mentioned that the solution to this differential equation winds up being y equals m over 1 plus a e to the negative rt. Now, if you're very sharp, you might have noticed that if you're very sharp, you might have noticed that this problem never tells us what R is. The other problems we had, it said the population grew at 2% rate or 3% rate or 5% rate, whatever it was, or the money in the bank was at this percent rate. We're not here we're not even telling what R is. Nevertheless, we could figure out R based on these values that are given to us and based on the formula that we have. But first things first, we're going to go alphabetical. We're going to start by solving for A. First, we're going to solve for A, and then we're going to solve for R. By the way, M, we don't have to solve for. We know that's 5,000. So in our example, Y is equal to 5,000 over 1 plus A e to the negative RT. And again, first thing we want to do is solve for A. And so what we're going to do is we're going to use the fact that Y of 0 equals 100. So we're going to use this fact first. So we're going to say 100 is equal to 5,000 over 1 plus A times e to the 0 power. In other words, 100 times 1 plus A equals 5,000. I'm going to divide both sides by 100. That just knocks off 2 zeros. And 1 plus A equals 50. So A equals 49. So here we go, we have A. So yay, we have A. Now we're going to use the fact that y of 1 equals 300 to find R. So we have so far, once we know A is 49, we have, again, using this equation right here, we're just going to fill in the A. So we know that Y equals 5,000 over 1 plus 49 times e to the negative RT. And we also know that when t equals 1, y equals 300. So I'm going to write 300 equals 5,000 over 1 plus 49 e to the negative r. Because t is just 1, so, it's just negative r. And I'm gonna write r times 1, so you know where that came from. And now we get 1 plus 49 times e to the negative r is just going to, I'm sort of cross multiplying now, is equal to 5,000 over 300, which is just 50 over 3. So I subtract 3 over 3 from each side. Minus 3 over 3. Oh, should be a minus sign. Minus 3 over 3. So we get 49 e to the negative r is equal to 47 thirds. Now I'm going, because 50 thirds minus 3 thirds is 47 thirds. Now I divide both sides by 49. So e to the negative r is equal to, well, let's see, what is 47? Let's just calculate that. What is 47 over, so 47 over 3 times 49 is, let me go on my calculator here. 47 divided by 49, 0.3197. Now I just take the ln of each side. So again, the ln of e cancel each other out because their inverse, whatever is called them. So that's just negative r is equal to the ln of 3.197. And again, going to my calculator, the ln of 3.197 is negative 1.1404. Let me just I just want to double check that just to make sure that's what I got. But let me just do it again. Point 3197, and we want the one, and that's right, negative 1.140 4. It's actually 0.37, but we're rounding, which means that r is equal to positive 1.1404. Now, finally, that means our formula now, our completed formula now is y equals 5,000. And again, y is the population, of course. I didn't, of a 1 plus 49 times e to the negative 1.1404 t. That's a big giant fraction. And we want to know what is the value of t when this equals 1,000. So this is going to be actually, I'm going to need another piece of paper for this because it's not that hard, but it's a few steps. I don't want to cram everything into one piece of paper. So let me just switch paper here, and we're going to okay. So we know now that our formula again is y equals 5,000 over 1 plus 49 e to the negative 1.1404 t. Now, they're giving us that y, so we know that y, so we want to find y of t equals 300. So we want to find the value of t that makes this true. So I'm going to put a 300 over here. That's the y value. Equals 5,000 over this whole ugly fraction. And now I sort of cross multiply. So I get 1 plus 49 times e to the negative 1.1404 t. Again, I'm trying to solve for t. Equals 5,000 over 300. Cross out a bunch of zeros. Subtract 1, which is the same thing as subtracting 3/3. So this equals 47 over 3. And now I'm going to divide by 49. So again, I get e to the negative 1.1404 t equals Oh, I think we had this fraction before, actually. Equals, let me just crunch this out in the calculator, and let me just, um, crunch, crunch, crunch. So it's 47. So 3 times 49, 3 times 9 equals, keep hitting the wrong buttons on it. 3 times 49. Right? Oh, you know what? I'm sorry. Uh, um, they weren't asking for, I'm sorry, they were asking for 3,000. Whoopsie. That's 3,000. I got to change the numbers here. That's 3,000. That's 3,000. So basically I cross another zero out. Sorry about that. And now it's, oops, that changes things, but we're okay. We're okay. Um, so let me just rewrite from here. So, let me just recap. So it's 1 plus 49 times e to the negative 1.1404 t equals 5/3. And now I'm subtracting 1, so it's like subtracting 3/3. So 49 e to the negative 1.1404 t is equal to 2/3. And but now I got to divide. Um, now I have to excuse me, I divide both sides by 49. So this is equal to, this is rough. Let me check my calculator. This is roughly equal to 0.01361, which means that e to the negative 1.1404 t is equal to, approximately, of course, 0.01361. And now I take the ln of each side. So I get negative 1.1404 t equals the ln of 0.01361. And that's equal to approximately, so I'm sorry, so t is going to be equal to, I just divide, t is equal to ln of 0.01361 divided by negative 1.1404, and that's equal to roughly 3.77. So it's going to take it's going to take 3.77 years to reach 3,000. So those wolves are gonna have to wait for a while. That's, what can I say? Sometimes you gotta be patient. I just want to mention that logistic growth is really good if you have it's a very good model for unadvertised sales, because a new product that's not advertised, that's going to have sales increase slowly at first, but then they're going to grow when the word of mouth spreads. Actually, let's see. We don't really need the paper anymore. I'm going to I want you to see my beautiful face here. So let me switch the camera. Yeah. So as I was saying, when you have an unadvertised sale, a lot of times you have a new product that's not advertised, right? And the sales are going to increase slowly at first. It's, word of mouth. and then they're going to grow as word of mouth spreads and people become familiar with the product. But then eventually the sales are going to level off when they approach, market what they call market saturation. What I find interesting about this is that I would dare say, I think it's hard to say that, but the internet, you've heard of the internet, right? And social media and all that kind of stuff, which didn't exist just, I don't know, a very short amount of time ago. A lot of you college students have known this stuff like pretty much your whole life, but really it's grown dramatically. Um, anyway, well, first of all, word of mouth spreads faster. Once you have social media and stuff, word of mouth you could like within minutes or hours, word of mouth. What used to take days or weeks, now within minutes or hours, word of mouth spreads really fast. Um, and but then again, there's also competition from online vendors. It's very interesting. I think it's had a very interesting effect, and which means we just got to figure as situations change, we just got to figure out more math, to accommodate or to approximate the situations. Anyway, this is it for 3.8. That's the end of chapter 3, and the next video we're going to go to chapter 4, which is very very dramatic and exciting. Anyway, everybody, we're going to see you next time. It's been loads of fun, and bye.